video recap of what we did today. So we did a quick recap on atomic physics. When the universe was made, three particles were made. They were the electron, the proton, and the neutron. And you'll see already I've drawn them different sizes. If we were to make a little table about their sizes, we would see that the proton is a mass of 1. Now in real life it's a mass of 0.00027 zeros, so physicists cheat, we just put 1. Same goes for the neutron, has a mass of 1. But the electron is far, far smaller. It's 2,000 times the size of the other two. So it's really, really small. But in terms of its charge, it packs a punch. Because if we do the charge, again, we cheat. We just call the charge of a proton plus 1, neutron 0, and the charge of an electron minus 1. So you can see, even though it's 2,000 times smaller, its charge is the same. And its location. Well, quite early on, atoms sorted themselves out into a nucleus in the middle, where the protons are situated, the neutrons in the middle, and then in the outer shells, at different energy levels, so we can have the S shell, we can have the P shell, that's where you'll find the electrons. And the whole of the periodic table is made of those three structures. And you just move on one up on the periodic table by adding another proton, adding another electron to cancel out the plus. So it's always neutral. And to hold the whole thing together, we have neutrons, which act like marriage counsellors. They act at holding those pluses together. They don't want to be near each other, want to head apart. The neutrons hold it all together. So in terms of location, we can say nucleus, and I think I spelled nucleus wrong, and nucleus again, and this one we've got the outer shells. And that's chemistry basically. Outer shells, adding electrons, putting them on, taking them off, that's chemistry. Physics, way more energy involved. We can access the nucleus and create atomic bombs. We figure out how stars work by messing about with the nucleus. So that was a quick update on atomic physics. In terms of writing out the periodic table, I'm hoping that most people are happy with this idea. Top number is always the mass of the nucleus. In our case, the one on my right is a mass of 4. And the bottom number is sometimes called the atomic number or the proton number. And it is what it is. Literally, you count how many protons there are, 2, write it in. And the whole periodic table works by just adding 1 onto this. So number 3 would be lithium, 3, and it would have 3 protons, but this time 4 neutrons, which would give us a total mass of 7. And you can just build a whole universe from those things. Next, static electricity. Well, if we look back at the electrons, there's 2 things about them that mean static can happen. One is, it's really, really small. The other is, it's in the outer shell. So, if we take an insulator and we apply friction, so we rub it with a cloth, we can actually remove those outer electrons, leaving behind the positives, and hence create static electricity. Now, it's got to be with an insulator. The reason it won't happen with a conductor is if you take away electrons from this region here, the other electrons are just going to conduct straight back in from the atmosphere, from the thing touching them, from your hand holding it. You just cannot charge up a conductor. It's got to be an insulator. You get trouble from those kind of things. If you're refueling a car, you can get sparks. When you're touching a car door, occasionally you get them too. So that's static electricity in a nutshell. The other thing we did was electricity. We're all happy with the idea from year 8 that, here's my light bulb, hopefully flashbacks to year 8. You may have been an electron lady. Electrons are given little bit blue pieces of paper and all the girls line up and each one of them is a little minus electron and everybody stands on the wire on the floor like so. And you stand there forever unless we put an energy source in. With that energy source, i.e. in this case the cell, we can define electricity. The cell gives the electrons electrical energy. And with that, they get a push and they start to flow. Now, we defined in year 8, 9, that the voltage was the amount of energy that the electrons carried, and the current, I, was the amount of flow. And if they flowed fast, it was a big current. If they flowed slowly, it was a small current. Well, if you look at an electron in real life, it's crazy. 0.0, and you keep going, and I believe it's around 10 to the minus 28 zeros. You could not count individual electrons. So instead we cheat. Just like our school is organised in terms of classes, we take our cloud of electrons and we lasso them into these things. Instead of classes, we call them coulombs. So one whole bunch we call 1 coulomb. Now I'm terrible at spelling this. I always get the O and the U and the M mixed up. Pretty sure it's spelled that way, but double check in your book. So there's a coulomb. Just like I can say 11 joule, and I know that I mean 32 people, I say 1 coulomb, I mean this many electrons. Now one little electron has a charge of 1.9 times 10 to the minus 19 coulombs. So it's really easy to work out how many electrons are in a coulomb. You just do 1 over 1.9 times 10 to the 19, and I think off the top of my head you get 6.25 times 10 to the 18 electrons in 1 coulomb of charge. So what does that mean to our model now that we're looking at? If we hop over, we can say, a bit like a conveyor belt flowing, here they are, here's my coulombs of charge. I can take out those lines, there we go. Each of my coulombs of charge can be carrying energy. Here we go. You may be hearing my 4-year-old screaming in the back, he's been naughty. So there's my coulombs, I've got 2 of them. Inside each one are all those electrons, and there they are carrying the energy. So let's have a look. What is voltage? Well, voltage is the energy, as we said, per coulomb. So just like if, there it is without a U, O-U-M-B. Just like we said classes instead of individual students, we say coulombs instead of individual electrons. But imagine we had 1 joule of energy spread out over that class. Same thing here. So 1 volt is literally 1 joule for a coulomb. 10 volts is 10 joules per coulomb. So it's really easy. We're just defining it in terms of coulomb. And what about if my conveyor belt was moving? So it's moving along, and say it's dropping off 1 a second. Well, we have a current, we have a flow. So we can define current, and current is the flow of the coulombs of charge. And it's very simple. In fact, press pause, test yourself. What do you think 1 amp could be? Pause it. Assuming you've not paused, I'm going to carry on anyway. 1 amp is just 1 coulomb every second. So 10 amps just means there are 10 coulombs every second. Now, knowing this, you can prove 2 equations correct. Let's have a look at the power equation. Power is current times voltage. We know power is joules per second. How many joules per second you're using. We did that in the PE lesson where we were looking at our average power output of step-ups. Well, if this equation is true, if I write current and voltage in terms of its raw units, they should cancel out and prove the power equation right. So, current. We saw current was a coulomb per second. We saw voltage was a joule per coulomb. If I now go through and I just cancel out the coulombs, I end up with a joule per second. So I'm proving the PIV equation right. If you haven't got this equation, by the way, whack it in a triangle. P-I-V, PIV. The other equation we can prove is called quit. Q. This is the amount of charge. Q is equal to current, I, times T. So let's have a look. Well, if my conveyor belt here, there's a coulomb, this flow is my current. Well, if I imagined a basket at the bottom collecting these, just like marbles falling in, I know if I have a current of 1, every second I'm going to get 1 coulomb every second. So 10 seconds later, I'm going to have 10 coulombs. If I had a current of 2 coulombs every second, then 10 seconds later, I'm going to have 20. And that's this equation, QUIT. Q-I-T. Goes nicely in a triangle as well. Q-I-T. And what it will let you do is it will let you work out total current, or even more useful, it will let you work out total charge flowing. So if we had a current, say, of 3 amps, and it ran for a time of 20 seconds, we would just do 3 times 20. We'd have 3 times 20, which is 60 coulombs of charge. And you'll see here I've used capital C. This is the reason why we don't use the letter C for current. It was taken by Coulomb. He got there first. We can rearrange that. If we knew how much was flowing, say 100 coulombs of charge sat there, and it flowed in, let's keep it simple, 10 seconds, then we can calculate the average current by just doing 100 over 10. And that concludes my lesson.